Hello everyone and welcome to today's video on science news. The video is inspired by the article I have talked about in the science newsletter on Friday. It is this article coming from the Institute of Organic Chemistry and Biochemistry of the Academy of Sciences of the Czech Republic from the group of Miroslav Polášek on using paramagnetic lanthanide complexes for encoding, storing, and retrieving information. Information, as you are aware, is a very important component of our lives today, of the technology that we use every day. But if we think about it on an even deeper level, information is also vital for life itself in the biosphere, for how our organisms reproduce and how they operate every moment. All of these events do require storage, retrieval, and copying of information. In fact, biology has, on the most basic level, solved the problem of storing and retrieving information by using nucleic acids, for example, DNA, where the information is stored in the sequence of nucleotide bases, which the sequence then codes for proteins to be produced, and so on. In fact, the storage capabilities of DNA are such and so good, even when we compare them to the typical technological storage options that we have, such as hard disks and flash memories. DNA still, in many ways, should be better than those. This sparks the interest of numerous people in developing information storage technologies based around molecules such as DNA. Other molecules and other basic principles that are investigated as having potential for being used for storing information on the molecular level are photoluminescence or single molecule magnets. All of these techniques have their benefits, but also downsides, such as the limited number of possible combinations and unique codes that can be generated with them, the need for rather low temperatures, difficulty of readout, and so on. One technique that allows us to read out information and from the molecular level out to the macroscopic is called nuclear magnetic resonance, and its cousin in the biomedical imaging arena, magnetic resonance imaging. Both of these use a combination of magnetic fields and radio frequencies to gain information about a chemical structure or even a structure of an organism. Importantly, the signal is read out on a scale and is in some way related to the chemical structure that we are looking at. Moreover, even for a given chemical structure in a given NMR experiment, the position of certain peaks can be affected by other factors. For example, whether a given molecule is on its own or is interacting with another molecule. All these things and others can affect how the signals will appear, where they will appear on the scale, and so on. And that is what the paper that we are looking at today is based around the fact that if you construct a molecule and add various elements to it, you can shift a signal of a reported group. In this case, the reported group is a trifluoromethyl group that is placed in a molecule together with two positions where paramagnetic ions from the lanthanide series can be inserted. And it should be noted that paramagnetic ions, such as lanthanides, have a very strong effect on how signals will appear in the NMR, both in terms of their position, but also in terms of their shapes and in terms of their other properties. What this work then goes on to utilize is the fact that their own molecules possess two positions where such lanthanide ions can be bound, and the fact that there are several elements in the lanthanide series, up to 12, that potentially could be useful for the purpose of shifting where the position of the trifluoromethyl group on the NMR scale could be found. This then generates a number of possibilities of the positions on the NMR scale where the signals can appear, and therefore generates this sequence or possibility space of unique codes that can be generated from limited amount of building blocks and starting units. One other thing that is demonstrated in this paper is the fact that what also matters is not only which of the lanthanides are used, which two are combined into those two positions that are available on the molecular reporter, but also the fact that it depends the order in which these two elements are bound, whether a given element is bound in position 1 or position 2 and its counterpart is bound in the other. That also affects, as can be seen here, where if two elements are used, dysprosium and holmium, we get different signals for whether holmium is bound in position 1 and dysprosium in position 2, or if the order is reversed. As you can see, these two combinations give us signals at different positions. And so based on of this, we can that possibility space of generation of unique codes can be then expanded. So we have our basic reporter molecule, which has two sides to bind two different elements. These then, the combination of these two metals then generate four what we can call codons, A, B, C, and D. And then if these codons then are mixed, or we generate mixtures that contain from one to all of them, and that can generate up to 15 unique codes that can be read out. And of course, if we add further lanthanide elements, as has been done in this part, the number of possible codes, possible unique codes, grows even more. And so then, using this, the authors have demonstrated the possibility to encode into a chemical composition of several physically separated layers in ASCII-coded message, in this case the word lanthanide. As a final demonstration of the capabilities of this approach, the authors utilize the cousin technique to nuclear magnetic resonance imaging, where again utilizing the four different combinations of dysprosium and holmium in their reporting molecule, generating signals at different frequencies. They encode an image-based message code into one plate. So overall, this is a very nice work demonstrating the possibility of using technique of NMR together with paramagnetism to generate a way of encoding and decoding messages on a molecular level. Thank you for your attention, and see you again next time.